Okay, so this is torque part two, and my name is Dr. Clyde Letzum. What I'd like to go over in this video is to go back and just refresh your memory as to what the definition of torque is, and then to look at torque, and this is also a refresher from part one, the introduction to torque. Also look at the torque with a perpendicular force, and then get into really what this video is about, which is torque with a non-perpendicular force. Okay, so let's go back and refresh our memory as to what exactly the definition of torque is. So torque again, and we use a uh, Greek letter tau to represent torque. Torque is a measure of how much a force tends to rotate an object about a pivot point, or we can call that pivot point a point of rotation. And if you recall, we said that that force that caused the rotation is really the force component perpendicular to the moment arm. And the moment arm again is just that distance between the point of rotation and where the force is being applied. Now the key thing here that I'd like to point out is that it's the force component perpendicular to the moment arm. Okay? Okay, so in terms of our equation, if you remember, we said that tau is equal to force times the distance. Now, in the first part of this discussion, part one, the introduction to torque, I said that there was a difference between the x, or the multiply, and the star that we also use for multiply. In this case here, the x actually representing the cross product, okay? X represents the cross product. And this comes in really handy when you think about applying a force that is not perpendicular to the moment arm. Okay, so keep that in mind as we progress forward. Okay, so if you remember from what we talked about in part one, we said that the torque, and when we have a perpendicular force, if we have some body affixed, okay, fixed to some point, and we apply a force to that is d distance away from the a fixed point, what happens is that body tends to rotate. Okay, so in this case, this body will tend to rotate in this direction, and this body here, if it's affixed here and the force is applied here, and that distance between where it's affixed and where we have the force is equal to d, that distance equal to d, then this will tend to rotate going in this direction. Okay, and so that's if you apply a perpendicular force. Now, what happens if that application of that force is not perpendicular? All right, so what happens is again, we're looking now at this body and it's affixed at this point, and we have this distance in here, which is our moment arm. So that means our force is going to be applied at this point here. But in this case, again, remember, the force is not being applied perpendicularly to the moment arm, but instead is being applied at some given angle. Okay, it's being applied at some given angle. So if we want to figure out what the torque is in this case, what we would need to do, or one way that we can look at this, is we can find the moment arm that would be perpendicular to that force. So it would be d sine of theta, where that theta is the distance, or the angle, pardon me, between where the force is being applied and the moment arm itself. Okay, and so we would be finding the y component, if you will, of the moment arm, and that y component would be perpendicular to, okay, that y component would be perpendicular to the actual force, and that's what we have here. And so because of this, we may say then that torque is equal to the force that's being applied times the perpendicular component, if you will, of d sine theta, if we look at this angle here as being the angle, again, between where the force is being applied and the moment arm. So this is d sine theta, okay, d sine theta then would be the y component of D. So in this case here, D is our hypotenuse. We're looking at this angle here, and then this would be the y component of that distance. Okay, and we would end up getting the torque looking that way. Now, sometimes this is a little bit confusing to actually look at. I actually prefer to look at the find a torque using a different method, and that is to start off again with the body that we're looking at, and it's being affixed at this point, the moment arm being this distance. And remember, we said that the force is actually being applied in this area here. Okay, the force is actually being applied in this area here. And what we'll do, instead of applying or leaving the force vector right here, what we will do is we will go along the line of action and we will apply the force up in this area. Okay, so it's still within the same line of action, which means then it's practically the same thing. So this is what we mean by applying the force within the line of action. Okay, and so we apply the force is still being applied in this area here, but rather than putting the force vector here, we're actually putting the force vector here. And by doing this, then what we can say then is that that force vector has an angle of theta here between where the force is being applied and the x component, okay, of um, well, the angle here is actually the x component here. This x component f of cosine theta, we're actually going to find a theta between this angle here. This is the angle that we're going to look at, okay? The y component then of this force is actually f sine of theta, and you'll notice that that y component is actually perpendicular to the moment arm. So if we take the f sine of theta times that by the moment arm, that also would end up giving us torque, as we show here in this equation. So again, we didn't move necessarily the force. All we did was we had it in the same line of action, okay, so that its effect on the actual body itself is still the same, okay. The effect on the body here is still the same. Instead of putting the force vector here, we just moved it along the same line of action, put it here, and then we break that force vector into its components, and we found the angle theta here from the x component, and that x component has to be in line with the moment arm. It has to be in line with the moment arm, okay? And that's where we get the theta from. And then the y component itself would be perpendicular to that moment arm. And so then we would be taking that y component of the force and multiplying it by the moment arm, which will then give us our tau. Okay? All right, so this has been a presentation on torque part 2, and the presentation was mainly about how do we analyze and how do we find the torque of the system if we do not have the torque perpendicular. Torque is not, or pardon me, the force is not being applied perpendicular to the actual moment arm. Okay, and so that's what we did in this video. And my name is Dr. Clyde Letzum again. Please do look for my YouTube videos at www.youtube.com/CA Letzum PhD PE. Or you may actually find more videos on my website at www.clydeletzum.com. For additional physics and electronics or electrical engineering stuff, you may find them at both of these websites. Thank you.